Okay, I have provided the answer of solution of question 7 in the recitation answers, but I'm going to talk about it once more. Okay, so the pure copper has an FCC crystal structure with atomic radius 0.128. Shear modulus of copper is 46 gigapascals. In annealed condition, so annealing is a special process that is a heat treatment process that softens the material, reduces the dislocation density. The high temperature enables the diffusion of atoms and atomic processes that require high mobility and high energy. And if you take a cold worked sample, heat it slowly into the sufficient temperature, wait for a certain amount of time and cool it back slowly, that will be the annealed condition. So in annealed condition, the copper sample has a dislocation density of as such. Through wire drawing, which is a cold working process, this dislocation density shoots up to 10 to the power 14. What will be the shear strength of the cold work sample if the annealed sample has a shear strength of 16.65? The relation between dislocation density and shear strength is given as such. So there is not much to say about this question. This is going to be similar to the whole patch relation example. So the expression is directly given to us here. So first we need to find what this alpha is. Now, usually alpha is given as 0.5 for metals. The Burgers vector, that's the important thing. This is the length of the Burgers vector. For FCC structures, the Burgers vector is going to be A over 2 times, for all cubic structures, this is going to be A over 2 times UVW, which this is the most densely packed direction or the slip direction. Okay, so for FCC crystal structure, the most densely packed direction or family of directions is 110. Then the Burgers vector is A over 2 times, or not times, but the 111 vector scaled by this scalar. Then the length of the Burgers vector is going to be A over 2 times the length of the 110, which is square root 1 plus. It's the length of a vector basically. And for FCC structures, we know that A is 2 square root over 2 square root 2r. Since atoms touch on the face diagonal is A square root 2, and that's 4r. If you substitute the expression here, 2 square root 2r divided by 2 times square root 2 again, these 2's cancel, it's going to be 2r, the length of the Burgers vector. Then it's going to be 0.128 nanometers. 0.256 nanometers is the length of the Burgers vector for this copper sample, or FCC copper. Okay, so in the solution, I have taken this tau 0 as the annealed condition case. However, that is not correct actually. We need to calculate tau 0. So tau is going to be equal to tau 0 plus alpha g B square root rho dislocation. Now, in the annual condition 16.65, we don't know tau 0 is. This is 0.5. If you convert gigapascals to megapascals, that is going to be 46 times 10 to the power 3 megapascals. We know what B is. It's going to be 0.256. Let's convert it to meters. 10 to the power minus 9. And square root rho dislocation. And from here, since at the annual condition we know the rho dislocation to be 10 to the power 7, we can find tau 0 as, we find it to be 16.63 megapascals. So I thought I was wrong in assuming that tau 0 is going to be equal to annual condition, but it seems that I was actually right. So tau equals tau 0 plus alpha g b rho dislocation. So you can take this to be 16.65. Alpha is known, g is known, the Burgers vector is known. The dislocation density is given as 10 to the power 14. And if you calculate it, this turns out to be 17.53 megapascals. As you can see, cold working dramatically increases the dislocation density, and that in turn increases the strength.